The exploration of Mars in the 21st century has undergone a fundamental transformation, shifting the focus from the question of the presence of water on the planet to the analysis of its role in shaping landscapes, climatic cycles, and potentially biologically active processes. Modern data collected by NASA rovers provide irrefutable evidence that in the distant past, rivers flowed on Mars, large lakes existed, and complex river valleys formed. These findings not only confirm the presence of liquid water, but also reveal a complex and multi-phase history of the planet's hydrology, which continues to this day. The central element of this history is Jezero Crater, where the Perseverance rover is conducting a detailed study of the remnants of the ancient Neretva River Valley, which fed a lake inside the crater itself. Analysis of sedimentary rocks in this valley shows that they formed in an aqueous environment more than 3.5 billion years ago, which directly indicates prolonged exposure to water erosional processes. This discovery is one of the key ones, as it links the formation of large river systems with the accumulation of sediments in a closed reservoir, which is the basis for the creation of complex ecosystems. A detailed study of Jezero Crater has revealed clear evidence of delta formation on the western edge of the crater, which is powerful proof of the existence of a long-lasting lake. Initially, it was thought to be a typical delta, but a deeper analysis showed that it is more likely a high-velocity, steep-fronted Gilbert-type delta, characterized by periodic changes in flow energy. This conclusion is based on the analysis of textures and structures in the rocks, which show a transition from flat-inclined to concave-inclined surfaces and changes in lithology within a few meters, indicating fluctuations in water level and current strength. Similar, though less pronounced, evidence of lake basins has been found in another important region, Gale Crater, where the Curiosity rover explored the sedimentary rocks of the Murray Formation, which formed in a lake in the early history of the planet about 3.7 billion years ago. Curiosity's research also revealed 4 well-preserved systems of river terrace deposits on the slopes of Mount Sharp, which were deposited after the drying of Gale Lake during the period from the late Hesperian to the Amazonian time, indicating multiple, though later, wet periods. However, large-scale river valleys stretching for thousands of kilometers across the surface of Mars require a more complex explanation than the simple existence of lakes. Their formation occurred over a long period, estimated at several million years, and was episodic rather than continuous. This refutes previous hypotheses about a long-term warm and humid climate on early Mars and indicates that erosion processes were caused by short-term but intense events, such as glacier melting, volcanic eruptions causing massive snow melting, or intense storms. This picture is confirmed by stratigraphic analysis, which shows that the valleys formed on already existing terrain, destroying it and creating new canyons, indicating intense water flow impact. It is important to note that even seemingly simple structures, such as sand dunes, can have a complex history. For example, large rippled structures 1 meter in size, observed using the high-rise camera, are not shock waves but aerodynamic ripples that form under wind action in conditions of low atmospheric pressure. This demonstrates that to understand the history of Mars, it is necessary to deeply study even the most ordinary-looking elements of the landscape. In addition to direct evidence of stationary water bodies and river valleys, there are other types of water systems indicating the multifaceted nature of the planet's hydrology. In Jezero Crater, structures interpreted as inverted river channels were discovered, which are inverted imprints of ancient river beds where more durable rocks remained elevated above the surrounding terrain after erosion. The presence of several generations of such structures intersecting each other indicates several non-simultaneous episodes of water flow during the period from the late Noachian to the Amazonian time. In addition, chemical analysis of the Martian surface through spectroscopy shows the presence of various minerals indicating prolonged interaction with water. For example, diagnostics of water systems can be conducted by the age of rocks. Age maps obtained by the crater counting method allow classifying regions by epochs: Noachian, Hesperian, and Amazonian. In Noachian rocks, absorption bands of clay minerals are often observed, indicating prolonged interaction with water in a reducing atmosphere. In Hesperian rocks, sulfates predominate, indicating a more oxidizing and arid environment, while Amazonian rocks are characterized by iron oxides, corresponding to the planet's current state. Thus, the history of water on Mars is not one big water period, but a series of wet and dry epochs, each leaving its unique mark in the form of various minerals and geological structures. The types of water systems on Mars are diverse and include stationary lakes with sedimentary rocks such as clays and mudstones, deltas, and sedimentary layers, whose age is estimated at approximately 3.7 to 3.5 billion years, and they have been studied in Jezero Crater using Curiosity and Jezero using Perseverance. River valleys in various Noachian regions have an age of more than 3.97 to 3.18 billion years. Inverted river channels in Jezero Crater date from approximately 3.63 to 3.5 billion years in the Hesperian period to 1 billion years in the Amazonian. Subocean outlets are also present, although their details are less detailed. Hydrothermal systems manifest in minerals such as sulfates, carbonates, and phosphates with red reaction fronts, and their age is estimated at 3.8 to 3.5 billion years in Jezero Crater using Perseverance. This multifaceted picture of Mars' hydrology is crucial for assessing its habitability. The prolonged presence of liquid water, especially in stationary water bodies, creates the conditions necessary for the development of complex chemistry that could lead to the emergence of life. However, the mere fact of the presence of water does not guarantee the existence of life. It only creates a necessary condition. For this, a suitable chemical composition and energy resources are also needed. It is in this context that the study of organic chemistry on Mars becomes as important a direction as hydrology. The search for traces of life on Mars largely boils down to the search for organic compounds, molecules containing carbon that are the basis of all known forms of life. Modern research conducted by the Curiosity and Perseverance rovers has provided compelling evidence that organic chemistry is present on Mars, but establishing its origin remains one of the most challenging tasks in modern planetary science. It has been confidently established that organic molecules are present on Mars. The Curiosity rover first detected total organic carbon at levels from 201 to 273 parts per million in 3.5 billion-year-old lake clays in Jezero Crater. In addition, this device identified long-chain alkanes, which are the largest organic molecules ever discovered on the surface of Mars. These findings demonstrate that complex organic molecules could form in the conditions of the ancient Jezero Lake. Significantly more sensitive instruments aboard the Perseverance rover have allowed expanding the searches. Using a combination of the Sherlock spectrometer and the pixel X-ray microanalyzer, researchers detected signals corresponding to aromatic organic compounds, such as benzene and naphthalene analogues, in various samples on the floor of Jezero Crater. These findings were made in several formations, including maas, representing basaltic lava flows, and Neretva, an olivine cumulate formation, indicating that organics could spread throughout the crater. Moreover, in the sedimentary rocks of Neretva Valley, organic carbons were discovered associated with sub-millimeter phosphate nodules, possibly vivianite, and millimeter reaction fronts rich in iron sulfides, possibly gragite. These findings are critically important because they show that organic molecules are not just randomly present, but entered into chemical reactions with other minerals as a result of diagenetic processes in an aqueous environment. However, the presence of organics in itself is not proof of life. Organic molecules can form both biologically and through abiogenic processes, such as reactions in hydrothermal systems or meteorite impacts. Therefore, the key aspect is the geological context. Analysis of the data shows that organic molecules often correlate with minerals that are themselves products of water-rock interactions. For example, the detection of organics in association with sulfates, carbonates, and clays in the rocks of Jezero Crater indicates that it could have been created, or at least protected, as a result of water-mineral reactions. Diagenesis plays a key role here. Processes of crystallization of new minerals, such as sulfates or carbonates, can encapsulate organic molecules in their crystal lattices, thereby protecting them from further destruction under the influence of radiation and oxidants on the surface of Mars. This makes rocks rich in such minerals prime candidates for searching for preserved biosignatures. Despite successes in detecting organics, the scientific community has faced a serious obstacle that has become the subject of active debates. Early Sherlock results showed bright ultraviolet luminescent signals in some samples, which were initially interpreted as a strong sign of aromatic organic compounds. However, subsequent, more thorough analysis, including comparison of Sherlock data with pixel data and laboratory experiments, led to a radical rethinking of this conclusion. It turned out that these luminescent signals do not have a biogenic origin, but are caused by an admixture of trivalent cerium in Martian phosphates and sulfates. Laboratory analogues, such as apatite from the NWA 10922 meteorite, containing 20 parts per million of cerium, demonstrated exactly the same spectral characteristics, which fully explains the observed signals. This case is a brilliant example of the scientific process. Preliminary but incorrect hypotheses were tested, refuted, and replaced by a more correct model based on more complete data. It also highlights the complexity of interpreting data from rovers and the need for maximum caution in conclusions about possible biology. In addition, there is a powerful theory explaining how organics could survive on Mars for billions of years. It is related to reactive chlorine compounds, in particular perchlorates, which were first detected on Mars by the Phoenix lander and confirmed by Curiosity. These compounds, present in the regolith, photochemically generate gaseous chlorine dioxide under the influence of ultraviolet radiation. This gas easily penetrates into the depth of the regolith and is an extremely effective oxidant that quickly destroys organic molecules, such as amino acids. This means that any organics detected on the surface must have either arrived recently, for example with a meteorite, or been very well protected. Laboratory experiments have shown that aromatic organic acids, such as phthalic and mellitic, can be effectively protected from photodegradation if they are embedded in the crystal lattice of hydrated magnesium sulfates. In such conditions, they can retain their spectral characteristics for dozens of Martian sols, while pure organic substances are destroyed in a few sols. This theory of protection in minerals is one of the most likely explanations for how organics were able to survive and be detected by our instruments today. Various instruments and rovers have contributed to the understanding of organics. The SAM instrument on Curiosity detected total organic carbon and long-chain alkanes in Lake mudstones of Jezero Crater, indicating chemical complexity with possible abiogenic or biogenic origin. Sherlock and Pixel on Perseverance detected aromatic organic compounds in the Maz and Sierra formations, correlating with sulfates with an undetermined source. The same instruments recorded luminescent signals in the rocks of Jezero Crater, which were reinterpreted as caused by C3+ doping in phosphates and sulfates. In addition, they found organic carbon associated with phosphates and sulfides in the Bright Angel Formation of Neretva Valley, as a result of low-temperature diagenetic reactions involving organics. Thus, we confidently know that organic chemistry on Mars exists and is complex enough to support biological or abiogenic processes. However, without delivering samples to Earth to laboratories with more advanced equipment, we will not be able to give a definitive answer to the question of the origin of these molecules. All our current conclusions remain hypotheses that must be constantly tested and refined. Questions related to the search for traces of extraterrestrial life inevitably touch on an area where the boundary between scientific fact and scientific hypothesis becomes particularly thin. In this context, anomalies can refer both to technical errors and to potentially biological structures. Comprehensive data analysis allows distinguishing one from the other using rigorous scientific methods and contextualization. One of the most important lessons learned from Mars research is that not all strange data are scientific discoveries. Often they are the result of misunderstanding the physical principles of scientific instruments. A striking example is the problem with the PanCam camera on the MER Spirit and Opportunity rovers. When operating in the longest wavelength filter, light with a wavelength close to the silicon bandgap penetrated through the CCD matrix, scattered from its back side, and was registered in neighboring pixels. This led to reduced contrast, artificial increase in signal and shadows, and the appearance of false spectral slopes, which were initially mistakenly interpreted as signs of hydration or silica content. This case serves as an important reminder of the need for thorough calibration and understanding of the limitations of each instrument before making final conclusions. The physical phenomenon underlying this anomaly was thoroughly studied and described, which allowed developing a corrective algorithm that corrects distortions and restores true spectral data. On the other hand, some structures on the Martian surface do cause enormous scientific interest because their shape and location resemble microbial or other biological processes on Earth. One of the most compelling findings made by the Perseverance rover are the so-called leopard spots, unique mineral structures discovered on rocks. These structures, having a shape similar to some microbial structures on Earth, are considered the most convincing potential biosignature on Mars to date. Although this is not irrefutable proof of life, They represent a very strong hypothesis that needs to be thoroughly studied. Another interesting aspect is related to sulfate formations. Hypersaline sulfate deposits on Earth, formed about 6 million years ago, serve as an excellent astrobiological analog for Martian sulfates. These terrestrial deposits contain perfectly preserved, synchronous, hollow, sinuous microfibrillar remains of microorganisms, proving the possibility of preserving biosignatures in such conditions. This gives hope that if life ever existed on Mars, its traces could be imprinted in sulfate rocks, which are widespread on the planet. Other potential biosignatures are related to chemical processes rather than macrostructures. For example, in the mudstones of Neretva Valley, submillimeter phosphate nodules and millimeter reaction fronts rich in iron sulfides were discovered, which formed as a result of low-temperature diagenetic reactions involving organic matter. Although these processes can be both biological and abiogenic, their joint presence in a geological context, indicating the presence of an aqueous environment, makes them extremely interesting for further study. The combined analysis of Pixel and Sherlock aboard Perseverance is a key method for studying such objects. Pixel determines the elemental composition at the sub-millimeter level, and Sherlock identifies molecular bonds, allowing the study of chemical correlation between different components of the rock. This approach allows distinguishing, for example, sulfates from pyroxenes based on their elemental composition, which was previously impossible using only one instrument. Comparing various potential biosignatures discovered on Mars, it can be noted that leopard spot patterns detected by Perseverance in rock outcrops of Jezero Crater are interpreted as the most convincing potential biosignature, similar to microbial structures on Earth, but not proving life. Sulfate formations studied from orbit using high-rise and in situ by Curiosity and Perseverance in Gale, Jezero craters, and Olympia Planum are high-quality analogs of terrestrial sulfates with preserved microfibrillar remains of microorganisms. Mineral structures with phosphates and sulfides found by Perseverance using Pixel and Sherlock in mudstones of Neretva valleys in the Bright Angel Formation are the result of low-temperature diagenetic reactions with organics, with undetermined biogenic or abiogenic origin. Ultraviolet luminescence, recorded by Sherlock on Perseverance in Jezero Crater, has been reinterpreted as caused by an admixture of C3+ in phosphates and sulfates, not aromatic organics. Inverted river channels visible from orbit through CTX and Ka-Sis in Ruel Crater indicate multiple episodes of water flow, but have no direct relation to biology. Ultimately, the search for biosignatures on Mars is a multi-level process. It begins with the detection of general signs such as water and organics, then moves to the search for more specific structures and chemical anomalies, and ends with rigorous testing of each hypothesis against alternative abiogenic explanations. Even the most convincing anomalous signal, such as luminescence, may turn out to be not biological but a chemical effect, as in the case of cerium. Therefore, the scientific approach requires maximum humility in conclusions and readiness to accept new data that may completely change the current understanding. Potential biosignatures, such as leopard spots or structures in sulfates, are at the forefront of this science, representing the most realistic chances of finding evidence of life on Mars if such exists. The search for life on Mars revolves around several key scientific paradigms that attempt to explain how life could have originated and evolved in conditions radically different from those on Earth. These theories take into account all available information, from geological evidence of water activity to the chemical composition of the regolith. One of the most influential theories is the hydrothermal life theory. It assumes that life could have originated and thrived in deep, warm, and protected from radiation and oxidants hydrothermal systems that arose as a result of large impacts on the surface of Mars. Modeling shows that such systems in Jezero Crater could remain habitable for thermophiles for about 720,000 years, and in the larger Gale Crater, almost 2 million years, which is significantly longer than previously thought. These systems could serve as a kind of arena for life, providing heat, energy, and protection for hundreds of thousands of years after the impact. The sulfates and other minerals found in Perseverance rocks, formed as a result of water-rock interactions, may be direct traces of such hydrothermal processes. Another central theory, the lake life theory, directly relies on compelling evidence of stationary water bodies, such as the lake in Jezero Crater and the lake in Gale Crater. This hypothesis asserts that life could develop in these ecosystems, using available chemical energy sources and nutrients dissolved in water. The presence on Mars of clay minerals, sulfates, and carbonates, which are ideal for creating complex chemistry and protecting organics, supports this theory. If life originated in a lake, its traces could be imprinted in sedimentary rocks that formed over years, creating ideal conditions for preserving biosignatures. The third important theory, which became relevant after the discovery of the high reactivity of the Martian regolith, is the mineral protection theory. Given that the surface of Mars is an extremely aggressive environment, subject to constant exposure to radiation and oxidants such as perchlorates, this theory assumes that any biomass or organics must have been immediately protected from destruction. The most effective means of such protection could be sulfates, carbonates, and clays. These minerals can incorporate organic molecules into their crystal lattices, creating microscopic capsules that protect them from the external environment. This theory finds confirmation in the fact that the most interesting organic findings often correlate precisely with these types of minerals, and laboratory experiments demonstrate that organics inside sulfates can survive under Martian ultraviolet radiation. Despite progress in understanding conditions on Mars, there are a number of serious obstacles that complicate the search for life. The main one is the high reactivity of perchlorates and other chlorine compounds in the regolith. As already mentioned, these compounds under the influence of ultraviolet radiation generate gaseous chlorine dioxide, which is a powerful oxidant capable of completely destroying organic molecules, such as amino acids, even at a depth of several centimeters below the surface. This means that any organics that can be detected today must have either arisen recently or been very well protected. Another factor is the chemical oxidizability of the regolith itself. The Viking lander back in the 1970s obtained ambiguous results in its biological experiments, which are now mostly explained by the reaction of perchlorates with organics rather than life. This emphasizes that even if life once existed on Mars, its traces could have been completely destroyed on the surface. In addition, there are problems with interpreting data from rovers. For example, analysis of Curiosity rover data on methane concentration revealed potential systematic errors in the measurement method. The method used by the tunable laser spectrometer averaged methane concentration using 3 separate spectral lines. But analysis showed that results for individual lines can vary greatly. One may indicate detection, another not, while their averaged result still gives a positive value. This indicates that the system may mask systematic errors, requiring additional verification and revision of the interpretation of methane data, which is one of the key biosignatures. Finally, it is important to understand the time frames. Most evidence of water and organics relates to early Mars in the Nochian and early Hesperian periods, when conditions were likely more favorable for the origin of life. However, after that, a climatic collapse occurred, and Mars became colder and drier. It is important to understand how long ecosystems could survive in later epochs, and whether there were any microclimatic or hydrothermal oases that could support life for most of the planet's history. The answer to this question requires a deeper understanding of Mars' geological and climatic history, which is still in the stage of active study. Summing up the entire array of provided data, it can be confidently said that modern Mars science has moved from the simple question, "Was there water?" to a much more complex and multifaceted one. What was the full cycle of hydrology, chemistry, and geology that could allow life to originate and develop? And have any traces of this process been preserved? Analysis shows that Mars did have all the necessary components to create conditions suitable for life: prolonged presence of liquid water, complex organic chemistry, and diverse chemical energy sources. However, we cannot assert with absolute certainty that life ever arose there. All evidence remains indirect and requires further verification. Scientifically confirmed facts about water on Mars are exhaustive. They include detailed studied sedimentary rocks in Jezero and Gale craters, proving the existence of stationary lakes, obvious signs of delta formation, and countless river valleys testifying to episodic erosion. We know that water was ubiquitous on early Mars. We also confidently know that organic chemistry is present on Mars. We have discovered a wide range of organic molecules, from simple alkanes to complex aromatic compounds, in rocks more than 3.5 billion years old. We also understand many mechanisms that could protect these molecules from destruction, such as embedding in sulfates and carbonates. We have even discovered potential biosignatures, such as unique mineral structures, leopard spots, which cause enormous scientific interest. However, the key gap in knowledge remains: the origin of organic compounds and the nature of potential biosignatures. Current robotic instruments aboard rovers, despite their impressive sensitivity, cannot provide a definitive answer to the question of the biological or abiogenic origin of the discovered materials. They can determine the presence of certain molecules and their geological context, but cannot provide sufficient information for an unambiguous resolution of this issue. A striking example is the case with ultraviolet luminescence, which was initially mistakenly interpreted as a sign of organics, but was subsequently explained by the chemical effect of cerium in minerals. This case vividly demonstrates how the scientific process works. Hypotheses are tested, errors are corrected, and understanding of the world becomes more accurate. That is why the future of Mars research and the answer to the main question about life on it lies in human hands. The only way to obtain definitive evidence is to deliver Martian samples to Earth laboratories, where scientists can use ultra-sensitive instruments unavailable aboard rovers. The Mars Sample Return Mission is the logical culmination of decades of research, and represents a joint effort by NASA and ESA. The Curiosity and Perseverance rovers, as part of their sample collection program, perform the first, most important part of this mission. They collect and hermetically seal in tubes samples of soil and rocks from various geological units and times. For example, Perseverance has already collected numerous samples, including sedimentary rocks from the Delta and Neretva River Valley, as well as samples from different formations, Maz, Sayera, Shenandoah, which together cover the geological history of Jezero Crater from about 3.2 to 4.1 billion years. These samples, each with complete geological documentation, will be left on the surface of Mars for subsequent retrieval by a new generation rover and return to Earth. In conclusion, it can be said that we stand on the threshold of one of the greatest discoveries in the history of science. We already know that Mars is a world with a rich and complex history, full of water and chemical processes that could support life. We have discovered the key building blocks that are the foundation of life and even hints that they could be organized into complex structures. However, the final answer to the question of whether there was life on Mars depends on us. We have already begun collecting evidence, and in the coming years, we will be able to analyze them in laboratories to learn the truth about our neighbor in the solar system.